Hello and welcome back. Alright, in the last video we talked about data types. We talked about how they're stored in memory as binary representations. And in this video I told you I would show you how some of those values are actually stored. Namely, how integers are stored in binary format. So, in order to actually convert a number from binary to decimal, we need to know how bases work. All of you are actually pretty familiar with base 10, and so you probably don't actually think about what goes into the composition of a base 10 number. So if we have our number 212, and we remember back from our elementary days of mathematics, we know that the rightmost column is the ones column, this middle column is the tens column, and the far left one here is the hundreds column. So what does that really mean? Well, it means that 212 is actually made up of the sum of three different numbers. And those numbers are 2 times 10 squared, plus 1 times 10 to the first, plus 2 times 10 to the 0. And so what this is actually on the left, 10 squared is the hundred columns, 10 to the first is the tens column, and 10 to the 0 is the ones column. So that's where the names actually come from. And so we can actually extrapolate this out into a generic formula for converting a number from any base and get that representation in base 10. And so that generic formula is going to look like this. A lot of subscripts, superscripts, don't let them throw you off. It's really quite simple. So you get the digit on the leftmost side times the base of whatever base you're in to the power of that position. So if we actually jump back over, for this example, 212, 2 is the digit, n is 2 because it's the third value, and we actually start counting from 0. So the digit at the third spot is 2, the base is 10, so we're going to raise that to the second power, and then we continue on our formula until we get down to 0. So that's the generic formula. A lot of people don't actually get too confused when they're working with base 10, but all of a sudden when they switch to like base 2 or base 16, they get really confused for some reason. But just remember that basic formula, that the columns are all just sum of a certain part, and you'll be fine. Alright, so let's convert this string, or this integer stream right down here, into an actual number that we know what it means. So let's turn it into a base 10 number. So all the leftmost digits, well, the left 24 bits are 0, just to make this example simple, so we'll focus on the rightmost 8 bits. And I left out the zeros calculations because, well, they're 0. So our number that we're going to be looking at here is 00101101. And so what that is that's actually the sum of this string down here. So we got the sixth column, which is the fifth place, 2 to the fifth. So we have 1 times 2 to the fifth. Then we have the fourth column is 0, so we don't ignore that. Or sorry, the fifth column is 0, so ignore that. We have the fourth column is 1, which is 2 to the third. So we have 1 times 2 to the third down here. The third column is 1, so we care about that value. So we have 1 times 2 squared. The second column is 0, so we don't care about that. And the first column, which is 1, so we do care about it, is 1 times 2 to the 0. And so if we actually calculate those values out, 2 to the fifth is 32, 2 to the third is 8, 2 squared is 4, and 2 to the 0 is 1. So this big long number represents 45. There's an awful lot of writing for 2 simple characters, but in a computer, that is the fast way to actually deal with those numbers. So I hope that made sense. I kind of went through that a little bit fast. Let's just zoom back over here. Remember, we start at 0 when we start counting, so if we go to the rightmost bit, we have the 1, so that's 2 to the 0. There's nothing in the second spot. The third spot has 2 squared right here. This is 2 squared. because we go 2 to the 0, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth, 2 to the sixth, 2 to the seventh. All right. So I think that makes sense. Really, it's just best to write down some practice problems to work those through, but that's the basic concept. And feel free to pause and rewind and watch that as much as you need to. All right, so that was a positive integer. How do we deal with negative integers? So let's take a look at the value 1 and how we actually might turn that into the value of negative 1. So our first approach is we could use the leftmost bit, this guy over here, as a sign bit, and let's see what happens. So if we had negative 1, which we're calling this negative 1, and we're going to add this to 1, we use addition rules the exact same way as we do in base 10. So you're going to get 1 plus 1, which is 2, so you carry a 1, and you get a 1 here, you get zeros all the way across, and then when you add 1 plus 0, you get 1. So that's not really what we want. So we know that we actually can't use normal addition rules if we were to set up our negative integers this way. And we could handle this, but then we'd have to look at the leftmost bit first and then do some special maneuvering to get things to work right, and we don't really want to do all that. What we want is we want addition rules to be as simple as possible. So what we know are the bottom row. We know that the bottom row needs to be 1 because we're adding 1. We know that the answer result should be all zeros. So we can actually use a trick called overflow. And what that ends up is that the top row is going to be all 1s. And so we'll take a look at what happens here. So since we're doing normal addition rules, we add 1 plus 1, and we get 2. Because 1 plus 1, 2 is our base. Just like in base 10, if we had 9 plus 1, 0 would be on the bottom and would carry over that 10. Same thing happens in base 2. We do 1 plus 1, which is 2, which is basically like our 10 in base 10, and so we need to carry that base value over. So 1 plus 1, the remainder is 0, and we have a base carryover of 2, which is represented as 1 right here. So this red 1 is our carry value. And so you'll notice something's going to happen here, that 1 plus 1 plus 0 is going to give us the 0, plus we're going to have to carry 1 over again. And so we're going to get this kind of domino effect of everything is going to get filled over to 0. And then we're going to hear at our 33rd bit, and the compiler is going to say, or the computer is going to say, you know what? Your integer value is only capable of storing 32 bits of information. So I'm just going to have to get rid of this extra 1 that you're going to carry over. Because this 1 is going to cascade over, and because each one of these is going to be 2. So this one's going to cascade over here. You're going to have a little carryover of a 1 here, and the compiler is just going to say, I can't do anything with that, so I'm going to throw that bit away. And that's what's known as overflow. So that, based on that little trick, negative numbers actually work out quite well. And this mode is called 2's complement, and this is what pretty much all the computers use. The addition rules are super simple. There's no special casing. And the nice thing about this is that you can actually convert from a positive number to a negative number super simple. So if we look at the top bit pattern, we see we have all 1s. If we look at the bottom bit pattern for a 1, we can say, we have all 0s except for that rightmost bit, which is 1. So it just happens to be that if you were to flip all of the bits on this top row and add 1 to that result, you would get a positive 1 value. Because all of the 1s would go to 0, so you'd end up with a whole row of zeros. You add 1 to all zeros and you get 1. And so that's this bottom row. You can do the same thing with the bottom row. You could flip all the bits, so you'd have all 1s going across here. This 1 would go to a 0, but you'd have to add 1, and so you'd end up with all 1s on the bottom. And so this actually works for all numbers, not just 1 and negative 1. If you have -5, you do the same thing. You flip all the bits in the bit pattern. So this is called the bit pattern, in case you're confused. This is the bit pattern of -1. So you flip all the bits in the bit pattern, and you add 1 to that value, and you can switch between negative values and positive values, and you can do that all day. Won't ever change the values of the numbers. You don't have to do anything special other than that. All right, so we took a look at, we briefly took a look at how you convert a binary number to a decimal. In this video, we talked about a little bit how bases work, so hopefully they'll be kind of comfortable with the idea of how you actually can change your binary numbers over into decimal. We're not going to spend any time showing how to go the other way. It's pretty straightforward, but we just don't really need to deal with that too much for this class. I just wanted to show you how the numbers are actually represented in memory, just so you can get a feel of how things work. And this is a good way to introduce you to that overflow concept of where if you add values that actually don't fit within your memory space that you're using for your types, that the extra data is going to get thrown away. So with that, thanks.